this segment, we're going to talk about sampling distributions. A sampling distribution is different than a sample distribution. It's very important to see the extra part of the phrasing of it. For a sampling distribution, you actually sample a size n over and over and over, calculate a statistic for each sample, and then look at the distribution of that statistic, not the individual numbers. So here, a sampling distribution is a distribution of a sample statistic. Now there's a few different sample statistics that we look at the distribution for in an elementary statistics course. The first one is the sample mean. So the sampling distribution of the sample mean, remember the notation for the sample mean is x with a bar over it. So you have to be very careful in your questions of whether they're talking about working with x, the individual random variable values, or x with a bar over it, which is the distribution or the values of the sample mean. So the sampling distribution of the sample mean x bar has a mean of mu, the population mean of the sample means, the distribution of the sample means, is the same as the population mean of the individual numbers. Notice the subscript is telling me that this is the population mean of the sample means, and without the subscript, it's talking about the population mean of the individual values. So the mean stays the same. And the standard deviation of the sample means, that sampling distribution, actually changes from the standard deviation of the individual numbers. But it changes in the situation where you take the standard deviation of the individual numbers and divide by the square root of how many were sampled when you got the distribution. So small case n, remember, is the sample size. Now shape. Whenever we talk about describe a distribution, we want shape, center, spread. So we already went over the center. The population mean of the sample means is the same as the population mean of the individual numbers. We went over the spread. The standard deviation of the sample means is the standard deviation of the individual numbers divided by the square root of the sample size. The shape for the sample means, however, you have two different scenarios. Now, if you know that the individual numbers had a normal distribution, then the shape of the sample means will be normal regardless of the sample size. So it's kind of like it gets grandfathered in. So the shape is normal if the distribution of x, the individual numbers, is normal. Now let's say that you don't know what the distribution of x is, or that you know it's not normal. Well, in that case, the central limit theorem kicks in. And it says if the distribution is not known for the individual numbers, or is not normal, or is not known, the distribution for the sample means is still going to be approximately normal when n, your sample size, is large. Now large is a very vague idea, but typically, or by the central limit theorem, as long as you have a sample mean a sample size that's greater than or equal to 30, so as long as you have 30 or more in your sample when you do this, then that's enough to have our sample means be approximately normal. And again, that's by the central limit theorem, and we just abbreviate the central limit theorem by CLT, central limit theorem. Now, let's see how we can apply this. Let's say we have the situation that the heights of men are normally distributed. Okay, so the individual numbers are normally distributed. That means that the distribution of the sample means will be normally distributed as well, no matter the sample size. With a mean of 70.7 inches and a standard deviation of 2.8 inches. They could either say it in words or they could do the symbols. So I phrased it when I was pointing to what the symbols are. Now this first part says describe the sampling distribution of the sample mean. So we want to describe shape, center, spread, the distribution of the x bars when we had that scenario. And here, if a random sample of 35 35 men was selected and repeatedly sampled, and I looked at all of the sample means of groups of 35 that were randomly selected with their mean height calculated. Well, for this, the first thing is, because the individual numbers were normally distributed, so will the distribution of the sample means. So the shape of the sampling distribution of the x-bar will be normal because the individual numbers were normally distributed. The center, mu sub x-bar, will be the same as the mean of the individual numbers. So it's going to be 70.7 inches. And the spread, I'll write that over here, is the standard deviation of the individual numbers divided by the square root of how many were in the sample. So that's 2.8 divided by, well, we randomly sampled 35 men and looked at the heights over and over. So square root of 35. And when you calculate that out, that's approximately equal to 0.47329. So I'll just write 0.47. So there's my shape, my center, and my spread. Now the next part is, what is the probability that a randomly selected man, so just one, so you're just having one x value, is taller than 68.4 inches? So when I want the probability that x is greater than 68.4 and it's normally distributed, we're going to do normal CDF on a TI 8483 calculator. Now remember, it goes low, comma, high, comma, mean, comma, standard deviation. This is the x's are greater than 68.4. And height is a continuous random variable. So I'll still use the 68.4 as my low value. Comma, high, we're going to go 1E99. The mean of the individual numbers is 70.7. And the standard deviation is 2.8. And when you calculate that, you get about 0.794. Now, this last part is where this whole idea of the sampling distribution kicks in. What is the probability that a randomly selected group of 35 men have not a height, but a mean height of 68.4 inches? So you're not looking at just the individual, you're looking at a sample mean of a group. So this is still a normal distribution because the individual numbers were normal. So I've got my normal CDF. The low is 68.4. The high is 1E99. The mean of the sampling distribution of the sample means is still the mean of the individual number, 70.7. But the standard deviation, that's the part that changes. It's the standard deviation of the individual numbers divided by the square root of how many were in the sample size. So that's about 0.9999. It goes on where it's just about a probability of 1. Okay, so again, this is an example of a sampling distribution, and specifically the sampling distribution of the sample means and its application that we have.